Okay. So I'm Raz. Actually, I'm a student. I'm doing my PhD in the Weizmann Institute with co-supervisor in the Hebrew University. So David Harel in Weizmann and Guy Katz in the Hebrew University. And my topic is really, at the heart of what I'm going to present here, which is aiding DRL, deep reinforcement learning, with rule-based, explicit rule-based languages or systems. I'm going to present a paper that was submitted to, or is going to be submitted soon to this ESEC FSC 2023. We did try to submit it before and were rejected, so that's probably a good paper.
Good luck next time.
Yes. Okay, so what we're going to talk today is I'm going to give a really brief overview of concept and prior works that will be needed to get better understanding of what we have done here. The main point is integration of scenario-based programming with DRL training loop. I'm sure everyone will, looking at the names, I'm sure people are aware of that, so maybe I'll run on that overview very quick. And then we'll, spend a little time on constraint deep reinforcement learning and the optimizations that we have developed in this work. And we're going to show, I'm going to show results that, using our methods, how we're doing. Throughout the presentation, feel very free to ask questions. If I'm able to, I'll answer interactively. Otherwise, we could take some questions at the end. But my preference is just to be interactive. You hear me well? You see the screen, right? Okay.
Yes.
Right. So state charts in a nutshell. If there's anyone that doesn't know what state charts are, please leave the call. No. Right. State charts in a nutshell, hierarchical state diagrams that allows you to present a state of a system in a very compact way using hierarchies and other means. I'm just pointing at a few notations that we are using. That that circled arrow point at the initial state, right? So B is initial state here. At that configuration, we have a a transition label, means there is event beta, and then and if you are in F, in any state in F, it doesn't matter in what exact configuration underneath. Make that transition to state B, and yeah, okay. Another interesting construct is a conditional transition. So if the event gamma happens and the condition C is true, then and you are in state A, F dot G, dot A, then take the transition, that transition. Hopefully people feel comfortable with this. Otherwise, we could spend more time on that. Scenario-based modeling. Yes. Okay. Another language coming from the same house, basically to describe behavior, but in a readable or more readable way to ease up the burden of defining system requirement specification or desired behavior. Just focusing on some construct here, right? So I had 3 scenarios, and now I just focusing on one. It's called add hot water from the classical paper. And what you see is that in that state, the system waits for event water low, and it says wait for water low. And when the event water low happens, then the system transitions, or that scenario, internal state of that scenario transitions to another state. And in that state, it just requests add hot. And you can see the sequence. It will request 3 times at hot and then get back to wait for water low event. The other scenario that I'm discussing here is called stability. That is showing different constructs. So by default, we enter that state that the scenario waits for add hot event and is blocking add cold. Blocking meaning that the system is not allowed to trigger event add cold. So once add hot happens, then that scenario, stability scenario, will transition to the other state in which it waits for add cold and while blocking add hot. That really is that stability, or ensuring that those events cannot happen. The same event cannot happen multiple times in the sequence. Again, I'm not okay. That language is very attractive for our work with constraint DRL training, being formal, fully executable, and really allows us to add more behaviors as we go, I mean, being incremental. And the fact that it is using kind of high-level language, or let's say domain-specific language, that allow to express constraints in a very, I would say, sensible or easy to grasp method. Comparing this to end-to-end methods that, trying to calculate a reward function that will capture everything that the system needs to be done through the mathematical formulation of that very complex formula. We believe that that approach have significant advantages, and we'll see this later on as when we discuss the constraint the CMDP framework. Okay, formal verification of DNNs and DRLs. Well, again, I think I'm going to skip a bit. This is really not the core of the concept presented in that paper, but we are leveraging formal verification in the work here to test and prove that some of the desired properties that we wanted the DRL agent to have are indeed happening. So I'm skipping this, just adding the note that the group in Jerusalem, Guy Katz lab, really pushed forward on that approach of how to do formal verification for DRL agents, right? It's not like a classifier that you want to prove. You do need to take into consideration some sequence of interactions with the system. It's not a single shot, right? Input, just give me the output on that activation of the network, of the DNN, rather a sequence of some behavior. Okay.
Last, can I ask a question, please?
Yes, please.
If you know that you want some constraints, I mean, if you want your network to guarantee this for some non-negative inputs, why can't you just let the network do what it wants and then just enforce this condition afterwards, like guard it? Why do you need to verify things? Why not just let it do what it wants and then override its rule, its decisions?
Okay. So I think it's a great question, because it really touches on this on this point that we are of that work here. I did not well, I discussed this, I would say, informally, but I did not yet prove that. I mean, officially prove that the claim that in order to get optimal policy, that so the optimal policy can be achieved through constraints on the the policy gradients, And however, if you just enforce that, embargo the action afterward, you probably will get a less optimal policy. So in different situations, just enforcing some arbitrary, clipping values or any other arbitrary enforcement does not leverage the whole, I would say, space, option space. It's just very strictly enforcing a certain operation. So maybe if the agent, we'll discuss this at the end, maybe, but maybe in this case, the agent had 3 actions, go forward, turn right or turn left. If you say in some case, well, I don't want to move forward, and then, okay, so what do? You need to arbitrarily choose left or right. And maybe if the policy, the policy that you are building, that you're training for, would have known that in certain situation it's not allowed to move forward, it would have chosen some probability distribution for going left and some other probability distribution for going right. And how can you know that probability distribution between left and right? Just arbitrarily afterwards, right? It's difficult to know that.
But you could, for example, every time that you ignore something that the network says. I mean, if I take the question forward, and I'm taking, okay, so let's indeed just override the rule, the what the network said, and then give a -1 on the reward or something, so some kind of a punishment on the reward function, then eventually the network will know how to do it efficiently, or it doesn't want to get a lot of punishments. So it's more a thought, rather than
yeah. I understand. Okay. I'm hearing you a bit truncated. I don't know if this is my connection or your connection, but I'm hearing you a bit truncated. But I got the most, I think, Achia. There are multiple options to do anything, right? I mean, you could hand program the controller logic. Yes, you could do many things. You could learn, so you could activate a post-activation, let's call it guarding wrapper, and use learning to learn the function, the policy function of that guarding wrapper. Of course, you can do anything you like, I guess, but it will be interesting to compare the envelope, the capabilities of one approach versus the other approach. But I don't know, I don't know.
Okay.
Maybe, right? It could be advantages one way or the other. I don't know.
I think this gets interesting, right? Because at some level we're saying let's close the door before the horse runs away, right? The stable door before the horse runs away, rather than say let's open the door and then let the horse run away and then say that's negative behavior, which. But I think the main thing would be to see what is the value we get from it, right? Is it going to improve the speed, the efficiency? What are we getting from it?
Yeah. Right. So, okay, I'll skip forward a bit so we could get to those points. Okay, of course, we can learn anything, everything with reinforcement learning. There's another question we can ask. We use policy function and not value functions. Although we use the discrete action space, we could have used value-based methods, but we believe that policy-based approach serve us better. Again, we did not prove that, but I think we did not prove that in this work. But we did chose policy based. We know that it's more expensive to train. You know, the downside to it, but I think there's also some upside for it. Especially looking on the challenge that we chose to deal with, which is robotic mapless navigation. We do have advantages with policy-based learning. I'm not spending time here. Right. So my my concern right now is that I'm not sure that I have a slide discussing exactly the points that we started to discuss relating to, you know, the qualities, like, you know, the safety and the envelope of what that method can do. But maybe, you know, I just finish presenting and we can discuss those. So I think we have two open points here to consider. One is what is the advantage of having the agent selecting a priori approved, you know, legal action, and then what's the value of what are we enabling overall with this approach? So what the benefits? So just technically, this is and again I'll skip a bit because I think the audience here you can free to, you know, just tell me to spend more time on any slide, but otherwise I think I don't want to just take the time that we don't need for. Everybody understand that, of course, and we just integrated the scenario-based program into the the DRL environment step, allowing us to run every time step the whole scenario-based model on a superstep regarding the agent action as external event that triggers the superstep execution. And so once the agent selected an action, we are running a superstep on the scenario-based model. When that superstep ends, we get back, we allow the environment to continue the execution, and we may choose to interfere with the reward or not interfere with the reward. And also during that, we also counting violations. But I'll show that. Yeah.
Raz, the scenario-based programming, the SBP program gets as input from the environment, it gets only the action and the candidate reward, or does it get also the new environment state?
It also gets the new state.
Okay, so it's missing here. So just
it is missing here.
Yeah. Okay. Okay.
Yeah.
Thanks.
Yeah. Well, correct. Okay, so I'm skipping this. We you know, we map the DRL agent actions to event in a scenario model, so we know how to act about it. And we saw, I mean, in previous work, we only modified the reward, but in that current work, we also counted directly the rule violations, and we showed that this has really high impact. Just to explain that, I'm going to just skip to you know, spend 2 slides or so on constraint MDP. So in constraint MDP, what we have is basically an optimal policy, right? We want to maximize the reward on the trajectory overall, while adhering to the constraints. So the constraints are expressed in a way that we have for each of the constraint, the ith constraint have some threshold, you know, the ith constraint, that the requirement in that for the policy to be valid is that the violations over the trajectory, the number of accrued violations for rule I are less than the threshold allowed for those for that rule. So for example, for rule number 5, it could be allowed to have 7 violations during a trajectory, which is okay. Above 7 is not allowed, and then it will be penalized. So we did, of course, that's known in the literature, some very, I would say, known manipulation, basically getting to the formulation that you want to maximize the reward. I'm sorry, you want to minimize that and maximize that artifact as it is with the minus sign. And you want to overall maximize the reward, the gain from over the trajectory. So we put some, of course, we did not, we worked further on that so-called vanilla policy update rule, and what we did, we've added a list of a few numerical calculation-wise things that we've done that really made that solution, I would say, very, very powerful. On top of PPO, so we have added that reward multiplier. I mean, there are some numerical problems, right? If you're just trying to solve that. One of them is that the optimizer will very quickly run that thing, right? Will focus on the cost very quickly, and you end up with a policy that really doesn't do any violations, but overall performance, the main task performance are very weak. So we've added that reward multiplier, basically binding, introducing this alpha, and I'll show later. So exactly, this lambda bound and normalization, those two things goes together. So we kind of balance here. This is arbitrarily health, or that's a kind of hyperparameter. Why health? We thought that it's equally important to have high performance on the main task and to have fully respect the constraints. We did not do sensitivity test. My gut feeling is that it's not very sensitive to this number. Once you put them together, even if this would have been a third, I think we would have got similar results. But again, we have not tested that. The bare fact is that the optimizer cannot just choose one side of that, one of those two factors, and just maximize or minimize the other. It needs to do them together because they contribute to the overall gain over the trajectories. We also allowed the policy gradient to learn first a policy. So we only started, we only allowed those lambda. The lambda are learned multipliers that multiply the cost factor, and we keep them at 0 at the initial training period. So I'm not sure exactly what's the threshold, but like after the performance goes above a certain, the main task performance goes above a certain threshold, then we unfreeze the lambda and we allow it to start playing in that gradient as well. And we control the learning rate, so we do not allow them to change too drastically. Okay, so that's really the heart of the optimization that we used here, and I'll show you how we define the main objective function and how we use the scenario-based program to define the cost, the CKs, the different cost factors over that sample. So why do we care at all? So those constraints are usually, will define some safety constraints, and really, it's very important to be able to get a method to train DRL agents that a priori that once you have the agent, it will follow some strict rules at all times. So it will never violate those. I'm not trying to convince you. I hope you accept that, in the different domains, you do need some rules that the agent will never violate. Mapless navigation, so not everybody know that thing. It is considered a difficult task in general. The point is that, unlike planning, that, given a map, you want to have a program that will find the best path. In mapless navigation, the agent needs to reach the goal only relying on its local observations. It could be all kinds of sensors. In this case, those are LiDAR sensors, but it can use also some other, in general, it can be cameras, it can be other things. And it only, its purpose is to get as effective as it can from the starting position to the goal without colliding with obstacles, with the walls or with obstacles that can be dynamic during the simulation, during the run, or static. But it's not important because it doesn't know the map of the scene anyway. So you just need to get to the goal effectively without hitting anything. Of course, there are many advantages in that. It's not dependent on the environment. It can run with static or dynamic environment. It does lead to high autonomy. So that's the challenge that we run the evaluations on. And this is a picture of the we used some simulation environment, but also we had this Turtlebot 3 very nice hardware that we ran as well. The DNN that we used for that is also kind of very well known, very simple. It has 9 neurons on the input, which are 7 LiDAR sensors that span 180 degrees. The front of, the whole front of the robot. And it also have a distance and a direction to the goal. Now, that distance and direction is only given at the beginning of at the starting of the run, by giving it the direction and distance to the goal, and then it did to calculate for itself all the time, like track the movement and know how much they still need to go.
I have a question. Can you hear me?
Yes.
So the technique you're applying for the search, if we assume like a space of 5 dimensions instead of 3 or 2, will it still work? Does it scale?
What search? What search?
The robot is moving, right?
The robot is moving, yes.
So the DNN is learning how to move it, right?
The DNN is learning how to navigate, how to get from the initial position to the goal position without colliding with obstacles or with the walls in an ineffective way. Yes.
So if I represent, if my representation of the search space is not physical, it's 30 dimensions.
Well, yeah, I don't know to answer that. We've done a similar afterward a test in 3D. So some not drone, some quadro chopper, I think, that navigate in 3 dimensions. This navigation is 2D basically, and we have just the option to go, to move ahead, turn left or turn right, and then you add another dimension, and you can go up or you can go down. when you are in 3D, and it performs. It shows similar. Properties. But I don't know if you go to 30 dimension. I don't know what will happen. I already know that it's not it's not easily extendable in the sense that we don't know what will happen in high dimension.
Okay.
But at least for 2D and 3D, we know that this setup is working okay.
Got you. Thanks.
But interesting question.
Raz,
Okay. Yes, please.
Can I have another question?
Sure.
So actually, I would. You suggested that the sensors include the GPS, but at least the robots that you have in the figures seem to be indoors, so GPS is not a relevant sensor, I believe. But I'm asking this because when you do not have some way to validate your actual location, a known issue with the navigation is that you have a location drift. So
Of
you
course.
believe that you are in one location and you are not there.
Of course, that's part of that system. It does suffer from that. Yes.
Okay, so no GPS. Okay,
No.
just wanted to make sure.
No GPS.
Okay.
We had only 7 LiDAR sensors. That's it. And it does have that drift. If you see the target, that's the real target, it's quite large. So I think it compensates for that. I mean, if it would have been a small point, then probably it would have been much more difficult to get to it because of that arrow drift. Okay.
Okay, thanks.
So so what we did, we have looked at some behaviors or considered what we would like the agent to, how we would like the agent to perform its task, and we have defined 3 key behaviors that we wanted to make sure that the agent follows. One is that we don't want the agent to do back and forth rotations in place. So just to explain the robot can move forward or turn right and turn left. When he turn right, is in the same position basically. It just its face right, and then when he will move forward, he will move to the right of what he was before. But the actual turn doesn't move. It only rotates the center, the face around the center of the object. So if the agent does the right rotation and left rotation, it's like he did nothing. Okay, he stayed exactly in the same, everything is the same state exactly as he was before he did this right and left turn. So, and wasted energy, he wasted time and energy. So we wanted to say, okay, that's not a reasonable behavior. So we don't want to waste time and battery energy. The second thing, we didn't want the agent to take long rotations, meaning if you need to, if you know that you need to change heading to some direction, please solve that through the shorter turn. You could always turn one way or longer turn the other way. So we wanted the agent to learn to always turn the short way. And so those 2 kind of constraints, I would say, we could discuss them as kind of safety or kind of constraint on the behavior. It's really a limiting the behavior of the agent. The third one, I think, is less safety and is more kind of active advice of how to do right, and that is to avoid turnings when the target is ahead, right? It's straight ahead from the agent and the path is clear. So if there's no reason to turn and you're just facing the goal, just move forward to the goal and don't make any turns. So that's the third scenario. And we were able to get in the end to, as I'll show you, to get agents that do not violate those rules. And we were able to, comparing to standard benchmarks and standard PPO, we were we were able to get on that task 87% success rate. With those scenarios applied, we got 95% of success rate, which is already showing some benefits, but on the main task performance. But we believe the most important advantages are the fact that we could show no violations of the constraints.
Last,
yes.
First, that's very impressive, these numbers. My question is, how did you come with these scenarios? Did you try without them and saw that the robot does these quite stupid things, and then so you decided to, why would I want to allow such unneeded maneuvers?
Right. So we have that walk. I did not say this initially. So that walk is together with Davide Corsi from Torino in Italy, and they have their large group of robotic experts, and we discussed, what kind of properties we could, make sense to do. So we started to collect that information, and we also ran simulations, just observing the agent behaviors. We did both, and eventually we came with those behaviors. We looked for more behaviors, but we found that those are I would say, the most significant behaviors that we want to constrain the agent about. Okay. Okay. So not sure if my screen. Okay. So very simple scenario. We adopted this language here, the graphical language. I think I found a reference to it. So there is one paper that defines such a mix of scenario-based concepts with state charts. So it's legal, but I think more than being legal, it's very clear, right? So you start here, you wait for any agent action. Any event, any such agent action that is mapped to external event, if the agent chose right, then you wait for forward or right, and you block left. And on the right, symmetrically, if you got here with the left, then you're blocking right because you don't allow the agent to do back and forth, left, right, or vice versa. And whenever you got move forward, then this automaton is reset, and you're starting again to block it. Hope this is clear enough, but feel free to ask if you feel okay. Similarly, avoid rotation. That example, left rotation, it has a similar graphics for the right rotation, and this is just the graphical means to explain the Python code that implements the scenario, so it's not really critical. But again, if you got left, then you're counting how many left turns there are, and if you got to the limit, then you block left, say no more, I don't allow this anymore. And if you got forward or right, you reset the internal state. I'm skipping the third one. I'm not skipping the third one. So Achia asked initially about the internal state, and here we just show that here there is, you see that condition forward leader state is clear, or target direction is straight ahead. Those are this is part of the state that the agency. Okay, so that this is really what another thing we've added in this work. Okay.
Wait, I have another question, please.
Yes, please.
Before you said that there is like a super step each time you get something from the network, and now I see that these threads do not communicate between them, and there are no additional events, you know, for the communication. You are directly reacting to the network or to the system itself. So for that, you don't really. I mean, it is called blocked, but it's not a blocking. It's just, you know, some output that you generate to the system, isn't it?
So you're right that there's no additional request events here. But those are the specific scenarios that we use. The framework that we created does, and the actual code that runs does enter that super step loop. In the cases here, it ran once and finished, but you know, we didn't limit that, or we were not relying on that. There will not be any more complicated calculation.
So my question was, do you also have? I understand it's not shown here, but did you run into examples where you didn't need the BP semantics? You know, the loop and the request and the blocking and the incrementality there, or because these are, I mean, it is BP, but these are just, you know, simple automata. I mean, you don't use the full power.
Correct. So we have used the incrementality. I'll show you just as we discuss results. We just added, we tested with one scenario active and then with 3 scenarios active, right? We just added to the scenario list 1 or 3 to execute. So we have used that aspect. We did not trigger the internal events. So we did not need to do that in that case study. So we could do even more, you're saying. That makes sense? Yeah.
Yes, yes. I wonder if it's helpful, the whole mechanism, or is it maybe this simpler solution is better because, you know, it's better to keep it simple.
I don't think so, because in the end, let me get back to that. I think that the key part is that each scenario is, you know, let's say scenario 1 and scenario 2 and scenario 3, each of them, when we executed, we defined this threshold, the decay threshold. So how many occurrences of this rule violation we allow in each run. And we had this indicator function. So, you know, it was 1 if every time the rule, the agent requested event that was blocked by a specific scenario, so indicated which scenario is blocking that event, and we incremented the cost relating to that specific scenario. This is completely incremental. We tested this with 1 and 2 and 3, and, you know, looking at the calculation below, I believe that it can easily scale to 10 editions. So you could have even 10 parallel scenarios. I don't know about 1,000 or 1,000,000. I don't think we will have all kinds of numerical problems, but up to 10, it's completely viable solution. And you don't care. I mean, you just define your scenarios, you plug them into that optimizer, you run it, and you get an agent that fully respects, that will find the policy, assuming it exists, right? If the inherent conflict, probably it does not exist. But if such a policy exists, it should be able to find such a policy that is valid and is optimal. So I think that that's really the heart of this whole point. And just skipping to the end, we have used formal verification to check that in deterministic policy, the agent fully respects the requirements. However, when we actually tested, we tested in stochastic policy. That means that we do not have, we cannot use the formal verification assurance. We only know that in high probability, they are respected. I'll skip to the results. So just really, those are the last slides, so we could expand the discussion afterwards. So the success rate, right, the blue is when we activated rule 1, and the other one is the standard state-of-the-art PPO running on the same problem. We used, the standard, you see here the mean and the standard deviation of 400 runs, something like this. So it's very clear, it's very distinct, the difference between the methods. When we only activated rule 1, you see below here for that rule back and forth movement. So you do see that the default, just the standard agent didn't care about that, and even though he was looking for optimal solution, optimality was somewhat not the best, because there are many occurrences of going back and forth, which doesn't progress anything. It wastes time and energy, and it doesn't do anything good. And we were able to get the violations below the threshold. This dashed line represents the threshold that we defined for the optimizer, and we see that it gets to actually 0 many times, and 0 or 1 cases, but we allowed up to, I think this is 3, just reading from here. And then when we activated all the rules together, again, comparing to the baseline, so that's the number that we quoted. It's hard to read here, but it's 87 versus 95% on the success rate. And you do see that the baseline for the back and forth violation and the 6 or more, like taking the turns that are larger than 180 degrees. So you see that the baseline do have that behavior in some frequency, and our agent, there's a lot of noise on the line. So there is a lot of noise on the line, guys. Okay, I'm not sure. Okay, so you do see that we were able to achieve. You always discuss what is more important, performance or safety properties, or some constraints. But using that system, we were able to get 0 violations or very low level of violations with high performance. And I do believe that because of the specific rules that we have used, leveraging expert knowledge, we were able to get those, that 95% success rate, which is better than if you're doing end-to-end learning without interfering.
Raz, your baseline was constrained. I mean, you did constraint reinforcement learning, and your baseline was without any constraints, or with a different type of constraints, for example,
without using the same. No, using the same PPO policy gradient without constraints.
Mm-hmm. So basically, continuing Gera's question, I think it would be interesting to see how is there any effect to giving constraints in the form of using scenario-based programming, or using, I don't know, some different language for constraints. I believe it will have the same effect. And the real contribution of using scenario-based programming or modeling, I think, is in the ability to provide modular specification. And if this is true, so the advantage of modular specification is really shines I would say, in places where the specification includes also what must not happen and not only what may or should happen.
So yeah, so I fully agree. The contribution, one part of the contribution, the main part is that numerical integration of the constraint factors into the learning of the policy gradient, for sure. That's so we did all kind of numerical things here which are new. So this is
Right.
those three factors are new. There were some other things in the literature, but not. And we're the first to introduce this balancing between the cost and the learning, that alpha factor, and to have this start the training with all those lambda freeze at 0 and introduce this learning rate over those factors. So all of that, I would say numerical things, numerical tricks, but very efficient in that case. And it really doesn't matter how you, in that regard, it really doesn't matter how you define the constraints and how you calculate, how you track the number of violations. That's completely separate. Additional contribution that I think is significant. I mean, coming from the world of formal specifications, I think that I can join the appreciation when you have complex specifications. Good luck to express the constraints, in general. And I think that scenario-based programs, as well as state charts, as well as additional formal languages, are very effective at expressing those constraints, especially that you could formally prove that your specification system is correct and consistent. And then if you have this method to leverage that specification directly into the DRL training loop, you have these guarantees that, well, the spec is correct and the implementation is correct, right? You close both ways. So I think that it's really those two factors, those two aspects that are important. One is the numerical one, and another one is the ability to use that language, a domain expert consumable language, and not some encrypted algorithm somewhere in some calculation function to try and define this, right?
Yeah.
Now,
thank you.
Perfect. So just well, I can just to show to Gera and everybody else. So just looking on one recording of PPO actor critic with no rules. If you look a bit on the behavior, you see that that agent preferred to turn right, even if it's doing 300. I mean, more than 180. It really preferred to go to do everything from the right. So okay, so that's without any rules. And another one with no rules that we just counted how many back and forth are done. You don't even notice that usually when you see such a session. And then when running the agent, again, with stochastic policy, this is not deterministic policy, this is stochastic policy. After we proved that with deterministic policy, there is no back and forth. That model will never in deterministic policy do that. I'm just running this until we will see finally that there is some back and forth. But you see the probability to have that violation is extremely low. I think that is that's the real robot, but I'm skipping this. I think that's enough. Okay.
Why we want to show, we used to say robot running. Show us while talking.
No problem.
While we ask questions.
So we were working very hard on this with the team in Italy, to cross-check. You see, he just stepped on the goal. To synchronize and do everything. Just realizing, I think 2 months ago, that we actually have some IoT lab in Jerusalem University with that TurtleBot 3 and everything, like, few physical instances of that just available 2 floors below us, which was fun. Anyway, yeah. Okay, so I'll be happy to take any more, discussions or questions, but also ideas on, where you see this useful or whatever.
Yeah, thanks, Az. Thank you very much. I think it's a very interesting talk. And I believe that we'll need to take the other discussions offline because we are about to finish our time. And I wanted to thank everyone for attending. And we have we reconvene in 4 weeks from now on the, I think the Monday, the February 7th, if I'm correct. Anyway, the first Monday of February would be our next meeting. And again, looking forward to meeting you again and to listening to this great lecture that we have here. Thanks, Saz.
Thank you.
Thanks, Raz. Thank you.
Thanks. Thank you, everybody. Bye-bye.
Bye-bye.
Thank you.